Hello and welcome to the first video in our Organic 3 lecture class. This is a brief overview on mass spectrometry. A couple of centuries ago we decided to introduce this topic in Organic 3. Most of the course, of course, is going to be the chemistry of organic synthetic reactions. But mass spec is really a key technique, of course, in a lot of areas of chemistry. This figure 12.1 was taken from the book, so it's got a lot of text around that in that reading section. It's got the basic layout of a mass spectrometer. One of the more important things to point out is the methods of ionization. And so that's really takes place in this entryway to the instrument. So there's a lot of different methods of ionization. What we're seeing here is an electrospray setup. But even this detail in this section isn't as fine as you would like. So you can Google image electrospray ionization and you'll get a lot more fine detail of that. Essentially, all mass spectrometry begins where you have your sample ionized using some kind of combination of high energy particles and heat. The particles go flying through the remainder of the instrument here. This is all physics, of course, not chemistry. There's a magnetic field. And the molecule is essentially broken up into fragment ions in this stage of the analysis. And they separate according to fragment size in the magnetic part. So when they finally make their way out and are detected and a spectrum is produced, you get peaks in the spectrum for fragments, and then initially, you would hope at least that you get a peak for the intact molecule, what's left of it. So different ionization methods in mass spectrometry give you varying amounts of fragments versus the intact molecule. Some harsher ionization methods don't give you much intact molecule left, but more fragments. And sometimes that's preferred, but often not. I'm going to go through an example of how mass spec could be used in more practical ways. And I'll leave you for more details on the method itself, instrumentation and all that in the reading if you want. This is from a natural products example from my own research lab. So we isolated this compound from this plant, and by NMR, the structure was determined. By extensive 1D and 2D NMR. And I'll emphasize that very few compounds can have the structure determined by mass spectrometry alone. In organic chemistry especially, NMR, one-dimensional and more advanced two-dimensional NMR techniques are what enables you to determine the structure. And the mass spectrometry really is to provide support for that structure. Or perhaps on occasion to resolve a conflict over perhaps, the location of a side chain like this, or maybe the alternate arrangements of one or two atoms or atom groups could be resolved potentially by mass spec. So this is what the actual mass spec data for this compound looked like. Of course, we knew the molecular weight and molecular formula from NMR, and usually you see the results like this. So the mass is given as the most likely mass. And so here it is as 477. You can basically call that grams per mole, but in mass spectrometry, the units are mass to charge ratio, so it's this odd MZ ratio, mass to charge, because the fragments as they fly through the spectrometer get charged. So here you have the formula that is the most likely formula presented by that exact mass. So we call this an exact mass if it goes out to 4 decimal places like this. 4 or more these days. Now, if you'll notice, the formula here actually, if you were to compare it with the structure, has an extra hydrogen. So the actual formula is C30H36O5. What we're seeing here is a molecular ion, usually M, plus H, and that whole ion has a plus charge to it. So that's our M plus H molecular ion. Why did it add a hydrogen as it flew through the instrument? Because we were doing the ionization in positive mode. So you can do that initial ionization like you saw above in positive mode or negative mode. In positive mode, it has the tendency to add a proton. One proton to the molecular ion. And in negative mode, it has a tendency to remove a proton from the molecular ion. So it's very normal to see an M plus H molecular ion in electrospray in positive mode, like you see there. Now, remember I said that the structure was determined by NMR, and that's true. Imagine if we didn't know the structure. Look at all these other ions. How confusing this would be to try to figure out which of those is your actual molecular ion. You really couldn't do it. Here's our molecular ion there. It is the strongest peak in this case, so that's encouraging. And more than that, there is given here in millidaltons, that's that 4th decimal place, molecular weight units, that's the error in this number, which is extremely low. What this says is that this molecular weight basically could fluctuate by 3 digits on this last decimal. And so really this data is really much more encouraging than what it seems here visually. Now, let's look at another example. This molecule has the molecular formula C23H22O7. That corresponds to a molecular weight of 410. So what we're looking for is a molecular ion of 410, and we don't see it. What the spectrometer is telling us is that the molecular ion is 433. However, it knows that a common phenomenon is the addition of sodium. And that has to do with, again, going back to the ionization method, where the sample itself is put into a matrix that happens to contain small amounts of sodium. So it's also very common to see the addition of a sodium atom in a molecular ion. So the actual molecular weight is 410. If you add a sodium ion to that, it's 23 more. So what we're seeing here is the mass plus sodium plus ion as our molecular ion. And again, with very low 4th decimal place error. 0.6 on that last decimal up or down, or 6 up or down on that last decimal. And of course it agreed with our NMR data, so it's really very supportive. In mass spectrometry can be used as a tandem method. This is really, really important in many areas of employment, in analytical chemistry, organic chemistry, and where those fields overlap. So a very typical thing would be at a drug lab, for example. Say you had a blood sample. What you're seeing here on the bottom is a chromatogram. So this is actually where, say, a blood sample is passed through a chromatography column, a very specialized one, creating bands as they pass through that are visualized as peaks, as you see here, once they come out the other end. So this technique is high pressure or high performance liquid chromatography. You might have encountered this already in one of your other classes. So each of these peaks, in theory, is a different molecule, different compound, present in the blood. Now, in a drug analysis, what's very typical is that they're looking for small components of the blood, lesser quantities of the blood, in the blood. So not the major materials in the blood, but maybe a peak like this that they happen to know is a drug like cocaine. So very small, present in very small amounts. They can hone in on that in the mass spectrometry part of the analysis, which is on the upper here. And so you can hone in on that, and from that same peak, as you see here, get a mass spectrum. Think of the power of this. You could get a mass spectrum of every one of these little components in blood and know what they are if it's a known molecule. Let me just emphasize that. So unlike the examples above, it has to be a known molecule. This won't give you the structure like NMR will. But given the retention time, say 8 minutes, as you see here, and the fact that you can get a mass associated with that peak at that retention time, and the mass spectrum corresponds to cocaine, you're getting pretty certain that this person had cocaine in their blood. But it's even stronger than that, because by analysis of the fragments in mass spectrometry, you can say, okay, here's my molecular ion for the whole intact molecule of cocaine, 303, molecular weight, essentially. The loss of this piece of the molecule creates this second fragment of 198. So the remaining portion of the molecule here has a molecular weight of 198. If you lose this fragment from the intact molecule down, what's left is this slightly smaller part of the remainder of the molecule that leads to the 182 fragment. Or perhaps the 198 is generated and then loses another oxygen to get to 182, which is a strong fragment. So when you go through and analyze the fragments, it gives further support for the structure of this molecule, cocaine. So in mass spectrometry, the molecular ion is very important, but also analysis of the fragmentation pattern can be very important and distinctive for that structure. So there's lots more that one can talk about with mass spectrometry. It's really valuable for molecules that have repeating units. So like, some kind of like polymeric material where you get fragments as each one in succession is chopped off. So you have your whole molecule weight, and then sort of fragments one by one get chopped off, and you can see those peaks appearing one by one in the spectrum. So things like polymers, amino acid chains of carbohydrates, all fall into sort of this very useful category of mass spectrometry. And that's it. That's my one video in our very first video. The remaining portions will be presented in the in-person part of the class and in probably two for sure, additional videos on this very first material. Well, maybe one. I'm going to hedge my bet there. All right.